Hello everyone, in this lecture we will try to finish the rest of the contents in the super pale mix design. In the previous lectures we have introduced the first two steps of super pale mix design, that is material selection and design aggregate structure. In this lecture we will focus on the last two steps, design binder contents and the moisture sensitivity analysis of asphalt mixtures. From the previous lectures we know that the second step of the super pale mix design is a design aggregate structure. We will design 3 trail blends with different gradations and fix the asphalt content. And then we will estimate the volumetric properties of the 3 specimens, and we will check the criterions for the volumetric properties. The one which will satisfy all the criterions will be chosen as the design aggregate structure. And this design aggregate structure will be applied in the third step, design binder contents. In the third step, we will use the aggregate with the designed gradation from the second step, and the aggregate will then be batched, mixed, and compacted with 4 different asphalt contents. We will then estimate the volumetric properties of the 4 specimens. With the results, we can calculate the asphalt contents at 4% air voids and also check the other volumetric properties, and that will be the major task in the third step. This figure shows the specimen prepared for the design binder contents. Basically, from the last figure, you can see that for each set of experiment, we will have 4 specimens, and each one will have 1 asphalt contents. In this case, that will be 3.8%, 4.3%, 4.8%, and 5.3%. We will use this information for the calculation of the volumetric properties. Here we can record the example in Note 16 for the design of the binder contents. From the second step, we know that the trail blend 3 will be chosen as the aggregate structure. And we will use the aggregate with that gradation. In the third step, we will choose 4 different binder contents, 4.2%, 4.7%, 5.2%, and 5.7%. For each specimen with 1 binder content, we need to estimate the volumetric properties, including the maximum specific gravity GMM at N initial and N design. Also, we have to estimate the air weight, VMA, VFA, and dust proportion, and we will use this information to determine the binder contents for the super pale mix design. In the design of binder contents, the super pale gyratory compaction test will also be conducted to measure the maximum theoretical density, which is usually referred as the maximum specific gravity under different number of gyrations. The figure here shows the results for the trail blend 3 with 4 different asphalt contents. Basically, based on the defined traffic level, we can find that the value for N initial is 8 and N design is 100. From the results, we can observe that with a higher asphalt contents, the maximum theoretical density, which is the maximum specific gravity, will be larger. In the third step, we will estimate an appropriate binder contents for the super pale mix design, and the result should come from the test. There are several requirements about the estimation. The first one is mixed air void requirement, where we want to find out the asphalt contents at 4% air void at N design regardless of the traffic level. The figure here shows the results from the test. In this figure, each point represents one combination of the air void and asphalt contents for one specimen. Here, the vertical axis is air void. We will have 4 specimens in the test. With that, we can find a line to fit to all these 4 lines. And then we can find out the asphalt contents at air voids equal to 4%. In this case, we find the asphalt contents at 4.7%. The second requirement we have to consider is a mixed VMA requirement. Actually, this requirement is determined by the nominal maximum aggregate size. Basically, with a higher nominal size, the minimum requirements about VMA will be smaller. With the nominal size of 9.5 mm, the minimum VMA is 15%, while if we go to the 37.5 nominal size, the VMA should be higher than 11%. In order to check the mixed VMA requirement, we have to estimate the value of VMA at the designed binder contents. From the mixed air void requirement, we find that the designed asphalt contents is 4.7%. Also from the test, we will get the measurements about VMA at different asphalt contents, which will be shown as the 4 points in this figure for the full specimen. Then we will apply the second order curve to fit to all these 4 points. And we will double check the value of the VMA at the asphalt contents of 4.7%. With that, we find the VMA as 13.2%. So that's the VMA we required for the super pale mix design with the desired asphalt contents of 4.7%. The next requirement is a mixed VFA requirement, and the range of the VFA is actually determined by the traffic level, which is measured in millions ESALs. If the traffic level is less than 0.3, then the range of VFA is between 70 to 80. If it's between 1 to 3 for the traffic level, then the range is 65 to 78. If the traffic is very heavy and the load is higher than 3, then VFA should be between 65 and 75. Similarly, we can estimate the VFA from the experiment. The figure shows the values of VFA under different asphalt contents for the full specimen in the design of the binder contents. We can apply the line to fit to all these 4 points. And then we will find out the value of VFA at the asphalt contents of 4.7, which you will find is 70%. So we have VFA as 70%. There's also one mixed requirement for dust proportion. In general, the dust proportion is defined as the percentage weight of 0.075 materials over the percentage weight of effective asphalt. For the 0.075 materials, it represents the particles with the size less than 0.075 millimeters. And for the effective asphalt, it represents the asphalt on the surface of the aggregate, or it could be represent the unabsorbed binder in the mix. For the requirement of dust proportion, we want the value to be set between 0.6 and 1.4. Similarly, we also want to estimate the dust proportion at the designed asphalt contents. From the experiment, we can find out 4 points for the dust proportion with respect to the asphalt contents, and then we can apply the line to fit to all these 4 points. With the asphalt contents of 4.7%, we can find out the value of the dust proportion. At the value of 4.7, from the line, we can find the dust proportion as 0.9. Finally, we want to find out the maximum specific gravity at the initial with respect to the designed asphalt binder contents. From the experiment, we can get 4 points about the maximum specific gravity with respect to asphalt contents. and then we will apply the curve to fit to all these 4 points. With the designed asphalt binder at 4.7%, we can get the maximum specific gravity as 87.1%. Then we can summarize the mixture property at 4.7% asphalt contents. For the air voids, we have already adjusted this one to 4%, which is the same to the criterion. And then for VMA, the adjusted value is 13.2%, which is higher than the minimum requirement of 13%. For VFA, it's 70%, which is just between 65 and 75%. The dust proportion value is 0.9, and it's also between 0.6 and 1.2. Also, we have the maximum specific gravity at N initial as 87.1%, and it's less than 89% as required. So we can see that this design is reasonable for the super pale mix design. The last step about the super pale mix design is the moisture sensitivity analysis. The procedure of moisture sensitivity analysis is defined in H2 test 283. Basically, the moisture sensitivity is measured on proposed aggregate blend and asphalt contents, which are defined in the previous 3 steps of the super pale mix design. The figures here shows the preparation and test in the moisture sensitivity analysis. In the moisture sensitivity analysis, we will prepare 6 specimens at optimal asphalt binder contents, which is defined in the 3rd step. The air voids is set at 6 to 8%. Among these specimens, 3 of them are vacuum saturated. The minimum saturation rate is 90%. Also, we will apply 1 freeze-thaw cycle to the specimen. We need to determine the indirect tensile strength for all the 6 of the specimens and identify the percent retained strength from the test. Here are more details about the sensitivity analysis. First, we will try to reproduce the short-term aging effect to the specimens. Basically, for loose mix, it will be placed in the oven at a temperature of 60 degrees for 16 hours. For compact mix, it will be stored at a temperature of 25 degrees for 72 to 96 hours. Also, in the experiment, we will prepare 2 sets of the specimen with equal air voids, and the air voids is set around 6 to 8%. One set is dry, the other set is saturated. The vacuum saturation will also be applied for the saturated specimen. To do that, we will first place the specimens in the vacuum chamber covering with at least 1 inch of water, and then drop the pressure by 26 inches of mercury for 30 minutes. And then we will tape the chamber to dislodge trapped bubbles and release the vacuum and leave in water for 30 minutes. After 30 minutes of the experiment, we can then determine the percentage of saturation. The equation here shows the calculation of the saturation. Basically, the percentage of saturation equals to 100 times D minus A over C minus B times E. Here, A is the dry weight of the specimen, B is the weight in water before saturation, and C is the SSD, saturated surface dry weight before vacuum. D is the SSD weight after vacuum, and E is the percentage of the air void in the specimen. In the analysis, we will also apply 1 freeze-thaw cycle for the saturated specimens. At first, the specimen will be stored at a temperature of minus 18 degrees for 16 hours, and then it will be soaked in the water with a temperature of 60 degrees for 24 hours. In the sensitivity analysis, the indirect tensile strength is estimated by the equation here. The strength S equal to 2P over pi HD. Here, P is the load applied to the specimen, and H is the width of the specimen. D is the diameter of the specimen. In the moisture sensitivity analysis, we also need to conduct the indirect tensile strength test. The test will be applied for all the 6 specimens prepared in the last step. Basically, we will apply the load to all the specimens and realize the deformation rate of 51 mm per minute at a temperature of 25 degrees. The figure here shows the process of the test. In the test, we have 3 dry specimens and 3 saturated specimens. From the dry specimens, we are able to estimate the average dry tensile strength based on the equation in the previous page. Also, we can find out the average wet tensile strength from the saturated specimens. With these two values, we can define the tensile strength ratio, which is the ratio between the wet strength and dry strength. We also want to make sure that the value of TSR is higher than 80% for the super pale mix design. Then let's recall the example applied in the previous 3 steps. We also conduct an indirect tensile strength test for the specimen with the designed aggregate structure and the optimal binder contents. With this test, we can find the wet strength is 721 kPa and the dry strength is 872 kPa. Then we can calculate the value of TSR as 82.6%, which is higher than 80%. Then we can claim that the design asphalt mixture exceeds the minimum requirements. It indicates that the mixture is appropriate for the road pavement design. Then we can summarize the example for the super pale mix design. Basically, from this design, we want to choose the appropriate aggregates and asphalt binders. For the aggregates, we will choose 10% number 1 stone, 15% 12.5 mm chip, 30% 9.5 mm chip, 31% manufactured sand, and 14% screen sand. For the asphalt binder, we will choose the optimal asphalt contents as 4.7%, and the asphalt binder is selected based on the temperature with the performance grade of 58 minus 34. In addition, the aggregate gradation is defined by the table on the right. Here we can see more details about the super pale mix design in Ontario. The first thing we want to check is the traffic levels defined in Ontario. Basically, in Ontario, the traffic is categorized into 5 types, from A to E. The traffic level A indicates the 20-year designed ESAL equivalent single axle loads. It's less than 0.3 million. This one will usually be some low volume roads, parking lots, driveways, and residential roads. In level B, the ESAL is between 0.3 to 3 millions. It will be some minor collector roads. In level C, the ESAL is between 3 to 10 millions. It will be some major collector roads and minor arterial roads. Level D will have the ESAL between 10 to 30 millions, and it could be some major arterial roads and transit routes. The last one, E, will have very heavy traffic. The ESAL will be larger than 30 millions. It could be some freeways, major arterial roads with heavy traffic, and special applications such as truck and bus climbing lanes or stopping areas. In Ontario, we also have some requirements about the aggregate properties in the super pale mix design. The table here summarizes the requirements and the different traffic levels defined in the previous page. The requirements is actually the same to the one we showed in Note 15. Basically, there are 4 requirements, including the minimum sand equivalent, the minimum uncompacted void contents for the fine aggregates, the maximum portion of the flat and elongated particles, and the minimum portions for the fractured particles in the coarse aggregates. The whole province is divided into 3 PGAC performance graded asphalt content zones. The figure below shows the division of these 3 zones. Basically, in each zone, we will have 1 performance grade for asphalt binder. If we are using the new hard mixed asphalt, or less than 20% of RAP, the recycled asphalt pavement. Then we can find the performance grade in the first row. For zone 1, the performance grade is 52 minus 34. In zone 2, it's 58 minus 34. And in zone 3, it's 58 minus 28. If we are using 20 to 40% of RAP, then we have to reduce both the average 7-day maximum temperature and the minimum temperature. In zone 1, it becomes 52 minus 40. Zone 2 is 52 minus 40. And in zone 3, it's 52 minus 34. The table here summarizes the adjustment about the performance grade in Ontario with respect to the traffic conditions. Actually, this adjustment is related to the road types. For urban freeways, we need to apply 2 grade increment from the standard performance grade, and each grade of increase represents 6 degrees. For rural freeway and urban collectors, we have to apply 1 grade increase from the standard performance grade. If the road is experiencing a very high percentage of the heavy truck or bus traffic at a slow operating speed, frequent stops and starts, and a historical concern with the instability routing, then we have to add 1 additional grade increase. For rural arterials and urban collectors, if the heavy truck traffic is greater than 20% of the total traffic, then we need to think about 1 grade increase of the standard performance grade. And additionally, we also need to think about 1 optional grade increase. For the rural collectors, usually we don't need to apply any adjustment, but if there's any additional conditions applied to the road pavement, then we have to apply 1 to 2 grade increase for the performance grade. This table lists the requirements about the asphalt binder with respect to different traffic levels in Ontario. Basically, we will need to consider the maximum specific gravity, GMM, the minimum VMA, and the range of VFA. Also, we have to consider the dust proportion. For the value of GMM, it has to be estimated at N initial and N design. For the minimum VMA, it is related to the nominal maximum aggregate size. The information provided here is actually very similar to the one that we showed in the previous lectures. In addition, the superpave gyratory compaction test will apply different numbers of gyrations at different traffic levels. In Ontario, for the traffic level A, the N initial value is set as 6, N design is 50, and N maximum is 75. By increasing the traffic level, the numbers of N initial, N design, and N maximum will all increase dramatically. So that's all about the lecture today. Thank you very much for your attention. With that, we have finished all the contents in the asphalt technology. In this topic, we spent a lot of effort for the introduction of super pale mix design. After the class, I hope we can go through all the notes and the videos together and try to understand the integration of the 4 steps in the super pale mix design.